So good morning everybody. So today we shall continue our discussion on optical fiber. With respect to instrumentation devices, optical fibers can be used as a optical fibers are used both for sensor and signal communication. So we will not discuss the detail of optical fiber here, just some of the key features of optical fiber we shall discuss before going to various kind of optical measuring principle applied for industry and other places, scientific and biomedical applications. So typically optical fibers are silica based because of the availability of low loss and low dispersion zone. Silica based optical fibers are commonly used. Though plastic optical fibers are also used in some special applications. Now for silica-based optical fiber, we have the loss profile. If we just draw it roughly, so typically we have a few low loss zones of optical fiber. This is dB per kilometer. Is 0.25, 0.5, 1, now in the visible zone, silica-based optical fiber has high loss and around 8.83 there is one low loss zone here. Oh, sorry. So this is around 830, there is one low loss zone, and then around 1.33 we have another low loss zone, and then this is 1 point, I think I have drawn little. It would be like this. Around 1.55 we have another low loss zone. Typically the lowest loss is around 1.55. However, there are optical fiber communications are also used at 1.33 because dispersion is minimum around this point. These are the peaks due to some trapped ions. During fabrications of optical fiber, OH minus ions are trapped, so that gives rise to the losses. Now, as you can see that this 1.33, 830 and 1.55, around this gen also we have abundance of 3,5 group of semiconductor sources and detectors. So thereby, that's why silica-based optical fiber is so popular, because its low dispersion transmission zone is matched with the popularly available sources and detectors of 3,5 group, whose fabrication process is also very standardized. This side we have high frequency scattering, and this side is infrared absorption tail. So there are two kinds of losses. Due to material itself, and waveguide. Materials loss is inherent property of the material, whereas waveguide loss depends on the geometry of the optical fiber. Waveguide loss is also dependent on the local bending Now, just maybe we can discuss just little bit about what we mean by waveguide and what kind of profiles that comes into play when light propagates through optical fiber. In most of the cases, optical fibers are circular in nature, cross-section is circular. Though there can be rectangular waveguides as well, but typically because of the drawing process, optical fibers are made circular. For circular waveguide, usually the wave propagation is written we will not discuss detail of wave propagation, just I am mentioning a few things for circular waveguides. Described by the distribution of the amplitude of wave as psi in terms of radius vector r, then the angle phi, distance of propagation z, and time t. For steady wave propagation of a frequency omega, we can write in this form psi r phi. So therefore the amplitude distribution is a function of the radius vector and the angle. Amplitude of light is a function of radius vector r and angle phi. So the differential equation correspondingly can be written in terms of the gradients in xy in terms of the amplitude variation. Often psi r phi is approximated as a product of two functions, as variation along r and variation along phi. So this is with the assumption that the variation of the amplitude along r is not dependent on the amplitude variation along phi. So then we can write these two in the product form. And if the guided mode is typically dependent on the wave vector k0, the wave equation is often written separately for r less than a and for r greater than a. So a is the radius of the core. So basically the equation is written in two forms, that for r less than a and r greater than a, and then it is solved. So I will not go into detail of those wave equations, but the solution is dependent on the value of a, and of course some parameters. Depends on the value of a. And the true diffractive index. That is for the core and cladding, N1 and N2. So if we define, say, two parameters, and expressed as Bessel's function, in terms of a N1 and N2. To simplify further, usually there are two intermediate parameters. I think three intermediate parameters. U, P, and W are defined. U is equal to A into K0 square, N1 square minus beta square. W equal to A into beta square minus K0 square N2 square whole to the power half, whole to the power half. As you can see, these have been defined taking into K0 is the propagation constant and beta is the longitudinal propagation constant. So ultimately, in optical fiber, the light goes through total internal reflections. But in terms of wave equations, this need to be satisfied in such a way is that the lengthwise component of the lambda should be sustained. And to sustain that, this some condition need to be satisfied, and those are defined in terms of UVW. Beta is the longitudinal propagation constant. And K0 is the wave vector. Free space wave vector, twice pi by lambda 0. So that's why it is multiplied by n1 to make it inside the waveguide. It can be shown that to have a solution which is of nature exponential of minus j omega t minus beta z to have a real value such that sustained oscillation is there. Or if there is sustained oscillations, actually wave is propagating lengthwise. So for that, the condition is that n2 square k0 square less than beta square less than n1 square k0 square. And as such, it tells that n1 is greater than n2. So that is the basic, in terms of ray optics, that is the condition for total internal reflection. So for this, U and W are real. So the solution, I will not write the solution, rather graphically let me show what it means. So if the waveguide diameter is very small and n1 minus n2 is also very small, so in such cases what will happen, that there will be a single spot at the output of the optical fiber if you project onto the screen. So this spot may look like this. So this is for one polarization of light, that is vertical polarization. If I take horizontal direction is x and vertical is y, then y hat is the unit vector in y direction. So y hat, and the intensity distribution is given by the Bessel's function of 0th order, J0 UR A. There could be another polarization, another solution will be there for the horizontal polarization. So two orthogonal solutions will come, that is except J0. UR is the U as a function of R. R is the radius vector, which is normalized with respect to the diameter A. Now, as the diameter increases, we will have physically what will happen as the diameter increases, the light can take many zigzag paths. So therefore, there will be constructive and destructive interference at the output. And if this one is limited, this refractive index difference and the diameter is limited to some extent, then there could be two such spots. Those are LP11, and the solution is given by the Bessel's function of the first kind. But these two spot intensity variation, if I take a cross section of that and plot the intensity, there is one negative maximum here, positive maximum here. So therefore, this is expressed, not only the Bessel's function is a monotonic function. So these two spots is given by the modulation by a cosine angle function. So phi is the angle. So if we take this one, then this is cosine phi is there. Plus, of course, we have another would be corresponding to the horizontal polarization mode. So single mode optical fiber usually have this profile, LP01 and LP10. Now if I twist that single mode fiber little bit, you will be able to achieve and project that output light, which should be of course a homogeneous distribution output at the input, maybe fed from a laser diode or laser helium neon laser or so. So in that case, you will be able to observe in the screen this profile. Now, because there are two spots, they can be distributed either horizontally or vertically. So the vertical splitting is given by the sin phi. These are known as the modes in waveguide. So modes means basically this beam propagates almost like a single beam corresponding to a one Gaussian profile. Okay. However, this one again can have another Gaussian profile. So there is some problem here, and anyway, I just okay. To explain it further, if we measure the light across the radius vector, that is the capital R, which is normalized, the radius vector normalized with respect to the diameter, so that is R by A. So if I plot the intensity distribution, sorry. So this is the LP01 mode where we have one peak, and for LP11 mode we will have now. What is the significance of this thing with respect to LP01? Significance with respect to instrumentation is that if we want the light distribution to be very uniform for a small spot, so then we have to use single mode fiber. So where only one mode uh, will be sustained, and other modes should be attenuated by twisting initially the fiber, or maybe by pressing the fiber through some micro bend, the higher order modes will be leaked out. So then the output intensity distributions will be pure. Otherwise, what will happen, that the illuminated site, if we want a very precise information, that will not be available because of a dark zone between two bright. So now in multimode fiber, such kind of peaks can be of the order of 50, 100, etc. I am here just shown 2, but it can be 50, and it can be as high as 50, 100 or more than that. For common multimode fibers of 50/125 micron, that is 50 micron is the core, and this is the cladding. Number of modes, that is number of maxima, number of minimum, number of maximum. Can be as high as 50, 100 or more than 100 also. So therefore, where we want a gross information, for such applications we can use multimode fibers, but for precise information derivation we have to use single mode fiber. So with that small introduction, we can start discussion on some of the applications of optical fiber. But before going to that, we can also discuss about the types of optical sensors. So we can go to a new section here, a new page. Optical sensor. So optical sensors can be of two types. They are of not two types. There can be of various types, but often they are made as intrinsic and extrinsic. So intrinsic means the optical element itself is a sensor, like the optical fiber or the source or the detector itself is the sensor. And extrinsic, basically we have a sensing element, a separate sensing element is present. So this is as a modulator. So we shall discuss a few examples. There are many types, but we will just discuss a few examples. Various applications are there. Applications are in industrial, scientific, biomedical areas. So first we will discuss one or two very and modulation wise, as I had discussed modulation wise they can be intensity modulated, intensity modulated, phase modulated, or polarization or frequency modulated. Or frequency modulated. So we shall discuss one of each, example 1 or 2. So first we will discuss about intensity modulated, because this is the simplest kind of schemes that can be made without much sophisticated source detector or other kind of sensing elements. These are based on some kind of change of light intensity related to the measurement. It could be due to absorption, it could be due to some reflection, or it could be some generated pattern, complete obstruction. So today I don't have much time, so I will just present a simple industrial scheme. Laser-based dimension measurement, that is used in rod, bar and wire industries, even for optical fiber as well. While fabrication of optical fiber is going on, the diameter need to be monitored constantly. So there can be basically it is a non-contact type of measurement. That is the advantage. So this is a polygon mirror, which is basically a meter cut in polygon. It could be a hexagon, pentagon, etc. As the mirror is mounted on a rotating body, okay, maybe a stepper motor or a motor whose speed is controlled and can keep a fixed RPM. So this reflection angle of the surface will change. So therefore it will create a sweep here, and the sweep is basically obstructed by a stopper, and in between we have a lens. So the focal point of this lens is here. So therefore this will make this diverging beam parallel. So the beam will be rotating from this side to this side. Okay. So this is a rotating beam moving parallelly. Now this beam will scan this surface. Basically it is a scanner which is used in many places. Now in between we have this. This is the cable or rod which is moving perpendicular to this surface at a speed. So now what will happen when we image this part onto a photodetector? This is rotating mirror. And if we see the output, okay, it is going out. Anyway, so this is the time which can be called as the stopping time, and this is capital T corresponding to the one scan, and Ts by T is proportional to the shadow time, which is proportional to the diameter. So these kind of schemes are used in cable industries, steel mills, where basically bars and rods are drawn. Now usually what they do to measure the circularity, they put two such schemes. That means two such measurements are put in X and Y direction, which are perpendicularly cutting this rod which is moving in the Z direction. Then we can know the ellipticity of the rod as well. So two counters or three counters can be set to simply measure this time, and which is proportional to diameter. The scheme is very simple and can be made very rugged as well. Now, in some of the modern schemes, this rotating mirror is no longer there. Instead, we can have a cylindrical lens here to make a diverging beam here. Now it is also there are line lasers available, so those can be used. And then The shadow time can be measured by putting a camera at this place instead of a photo detector, and then the shadow length can be measured by comparing the exposed bright zone and the dark zone. So, however, that is the resolution is limited by the resolution of the camera. The advantage of in this case is that we can have a very high resolution counters. Okay, so the time can be counted at a much higher resolution compared to the spatial resolution achieved by the camera. So that's why for precise measurement of the rod diameter and control, this is used. So thank you. We shall continue our discussion next time, tomorrow.